Hi everyone. Let's continue working our way towards finally having an official definition of what a derivative is. So in our preview activity, we looked at this function and we know we had points a, f of a, and a plus h, f of a plus h. And we'd looked at the secant line, so we connected the dots and said we could use that slope right there to estimate how steep the curve is. And the goal that we're going for here is being able to talk about how steep the tangent line is. So let's see if I can pick a good color here. Okay, so something like that. Your tangent line should match up with the steepness of the curve right at that point. So this is not supposed to be a secant line. I haven't selected 2 points. I've selected a single point and tried to match up the steepness of the curve at that single point. Okay, so the question is, how do we go from knowing how to deal with secant lines to getting the slope of the tangent line? And we've already kind of talked about the fact that the closer we move this second point in to the point we're really interested in, the better it gets. So if I move the point in a little bit, so this was my first one, this could be my second one, it's at least flattening out. It's still terrible if I'm trying to get this tangent line. I don't even have a negative slope left yet, but it's better. We could move into here and say this is 0.3. And that we finally at least have a negative point. We could move in here and say this is 0.4. And now it's starting to actually look kind of decent. So the idea is that we want to let the value of h go to 0. So we want the space between the 2 points to go to 0. So basically, we want to take the slope of a secant line, which is f of a plus h, minus f of a all over h, and we want to keep a the same. A is the point we're interested in. We want to let h get smaller and smaller and smaller. The way that we say that is with a limit. So we want the limit as h approaches 0 of f of a plus h minus f of a all over h. So this thing is called the derivative of f at x equals a. And there's a couple of notations, little shorthand notations for when we want to say find the derivative. One of them is to use f prime, which is just f with a little apostrophe, if you can see that. So if you see f with the little apostrophe right next to it, really pay attention for it. That's not saying plug a into f. That's saying find the derivative of f at a. And always, always, always remember that when I say derivative, that means the same thing as saying slope of a tangent line. That's the really big geometric connection that we want to always make sure that we're remembering. There is one other notation for this, and I like it. We could say, here I'm going to write it up a little bit differently. If we think about this as a change in y over change in x, so we could use a little bit different notation. That's what we're doing here. The slope of a secant line is a change in y over change in x. And then we take the limit as delta x goes to 0. We get a dy dx. So this is just kind of using our other delta notation to say a little bit of why it looks like this. So dy dx is also equal to that whole difference quotient. So I don't think I've mixed the dy dx into your homework so much in the first couple of sections, but I will, so I wanted to mention it now. So again, they mean the exact same thing, and you can, this is actually more of a Calc 2 notation, but I like it a little bit here. You can specify the x value. This is like an evaluate at x equals a. So both of those notations mean the derivative of your function f at x equals a. If this limit, so this thing is the key, no matter what, this is always what we mean. We have a couple of shorter ways to write that down so that we don't have to write that every time we want to ask you for the derivative. If that limit exists, which we know limits don't always exist, then we will say that the function is differentiable. So I guess that's like the verb that goes with derivative. Differentiate is the verb that goes with derivative. So if you can take the derivative, you'll know that because the limit will exist and you'll get a numerical value for your slope, and you could say that your function is differentiable. If the limit doesn't exist, then your function is not differentiable, and we'll get into a few of the details of when that might happen in a little bit, but just like I said, we know that limits don't always exist, and when they don't, that would mean your function's not differentiable. One last little reminder here on these upfront things before we get going. If your function is a position function, so it's giving height or distance or something along those lines, remember that it's the slopes, the average rates of change of that function will be velocities, which means the instantaneous rate of change, or f prime, the derivatives, will give instantaneous velocity. So if we want the instantaneous velocity when x equals a, we can just say find f prime of a. We don't need that IV notation anymore, which is why I wasn't super attached to it earlier. So to calculate, excuse me, instantaneous velocity given a position function, you should take the derivative of the position function at whatever time you're interested in. Okay, so just to make sure we're at least getting the graph of this, I'm going to sneak in one example here. Okay, so we have a function shown, and we're supposed to estimate each of the following things based on this graph. Let's see if I've got some good colors here. Okay, so first thing we're supposed to estimate is f of 0. So this is going to be, here, we'll use blue. F of 0, this is a y value, right? So we're going to go to where x equals 0, and we're going to go until we hit the function. And that little distance right there is going to be our y value, which looks like, this is a -1. It looks like maybe -0.4. Doesn't quite look like it's at -1/2 to me. Okay, so the first one is the y value. Second one, we want to find the average rate of change from x equals 1 to x equals 3 on the interval 1, 3. So here's x equals 1, here's x equals 3. The average rate of change is the slope of a secant line. So I'm just going to say, all right, let's pick the 2 points, and then we'll calculate the slope. So here's our line. That's actually a pretty nice line for approximating steepness. So we're going to take our second y value, which is 2, minus our first y value, which is -1. And we're going to divide it by our second x value minus our first x value. So 3 minus 1. Which is giving us 2 plus 1, so 3, over 3 minus 1, which is 2. You could also just count this out. You could say, okay, my slope is over 2 up 3, and that would give you the exact same result. Okay, so now getting into the new ones, that was sort of the warm-up part. What if I asked you to find f prime of -3? So again, really pay attention. You've got to watch for that little apostrophe. It's not a typo. F prime of -3, that's the same thing as me saying find the slope of your tangent line when x is -3. So I'm going to go over here and say, okay, x is -3, which means I'm talking about this point on the graph. And then I'm going to try and draw a tangent line. So if you have a graph, you shouldn't be using a secant line to estimate a prime. You should actually try and draw the tangent line as best you can. You will still be estimating. And then approximate its slope. What did I get? It looks like it's in the ballpark of 3. This one's sloping a little bit, but I would believe that. If I draw a line with a slope of 3 over 1 up 3, it looks like it does a pretty nice job of not crossing through and just matching that. So I'm going to say f of -3 is about 3. The slope of the tangent line when x equals -3 is about 3. And then just for good measure, let's look at one more. What about f prime of 1? So that's telling me that my x value is 1, which I've already looked at. So I'm talking about this exact same point that I used for my secant line. And I want to estimate the slope of the tangent line. So if I were to draw a tangent line here, it would be horizontal. I want to just touch at the very bottom there, which means f prime of 1 appears to be spot on 0, as long as I'm really picking out that bottom point. All right, thanks for watching.